Turning on. Okay, so welcome back from the weekend. I hope you had a better weekend than I did. I threw my back out and it was really bad over the weekend, but I believe everything's up to date on as far as all of our exam grades should be in, all of our homework grades in, and the activity grades should be in. So except for week 1 activity, which I'm going to hopefully do on our week 5, actually. I'm planning a kind of a Jeopardy thing where we all get to answer questions and participate. So that's where I'll get those additional 20 points for the group activity, okay? So online, you'll see that all videos through the rest of the semester are up now. As far as, you know, from chapter 9 on, those are all on there. They might not be in exactly the right order, so you might have to scroll down the playlist. So please make sure you scroll down the playlist. Some chapters are shorter than others. For example, chapter 10, the amine section, is actually fairly short. The benzene one is, I believe I have like 5 or 6 videos on this one because it's a little more complex. And so please look for all of them and make sure you check them off as you go. And then I also have all of my our in-class and goals are already from last week, already posted. In Top Hat, homework for chapter 9, which is benzene, and chapter 11, which is spectroscopy, is up. All the goal slides are up for those. I'm still working on the chapter 10 homework and self-test questions. I only have 3 or 4 questions on each right now, and I wanted to add a few more to give you a little more practice. And so as far as that goes, I'll probably be adding more to those tonight and tomorrow. So don't rush ahead and do the amine homework just yet. Give me a couple days on that one. But I do have chapter 9 homework done, chapter 9 self-test done, all the goals for chapters 9, 10, and 11, and I think even part of 12 already posted on Top Hat. So that means that, you know, you should have enough to get you started on this week, especially with chapter 9. Chapter 9 has some really interesting stuff we're going to go over today that has to do with the whole concept of why benzene's different than everything else up to now. But we're going to start with the mechanism, and some of the patterns in the mechanism should be the same. We just need to look at it kind of backwards. And so I'll get into that as soon as we get into the goal 1, which is, actually it's technically goal 2, the mechanisms and the reagents we'll use. Okay, let's see. So homework, self-test, goal slides, videos are up. Chapter 10 homework and self-test will be completed by hopefully Wednesday. So I believe that's all the administration I have today. Oh, one thing is I will not have a half-hour happy hour on Friday this week. They scheduled a faculty meeting on top of it. So unfortunately, I will not be able to do that. So, but those of us who were there this weekend, we had some really good ideas come out, and you'll notice I sent emails on Friday about group study sessions, about a couple different things that came out of that talk. And so I think overall that worked really well. And so go ahead and look at your Canvas page.
It's not working, or you can't do it right now.
All right.
All right.
Are you talking to me, or are you?
Bye, guys. Yeah.
All right. So maybe I should mute Paige real quick here. She doesn't know she's unmuted. There we go. So anyway, if you did have something to say, Paige, go ahead and unmute. But so let's see. So go to the Canvas page. There is already a discussion up about somebody trying to do a study session right after class today. and I believe they set up a Zoom. So if you want to join that or start your own or ask questions, go ahead and put your stuff in that section, that forum. I will not participate in that. This is for you to, you know, to kind of have peer-to-peer teaching and peer-to-peer learning. So I think that I will not monitor that, or, but if you have questions, go ahead and email me and I'll get to it. I do have a meeting this afternoon on
Oh, you did?
Yeah, because you know, we're like, oh yeah, that is true of each other. So,
Paige, are you trying to talk to
oh,
me?
I just,
Paige.
is it Mark? Okay, yes, you're right. I was like, so
Somebody call her.
I'm going to mute her again. I think she unmuted by accident. Okay, so that being said, Lauren, you're unmuted. Do you want to mention something?
No, I was just talking about Paige. I
Oh.
will mute myself again.
Okay. So, all right. So that being said, again, go ahead and chime in, or I have the Zoom chat up here, so I can go with that. I'm going to start with Chapter 9, Benzene and its derivatives. My goal 1 is going to be, well, what is aromaticity? And how do we recognize it? And that's what I'm going to start doing by sharing my screen. Let's see if it's going to let me do it. It's behaving today. That's wonderful. Okay, can everybody see the screen with the Chapter 9, Benzene and its derivatives? All right, great. I'm going to move the videos over here so I can see you flailing your arms, but I can't. It doesn't distract me as much as normal. So, all right, there we go. Okay, so the first thing we want to talk about in benzene and its derivatives is, number one, benzene's different. We said earlier when we talked about our alkenes that this is one of those subclasses of alkenes that behave differently than everything else. And so we wanted to talk about it separately. And so the whole concept there is, what is aromaticity and why does it make things react differently? And so that's what we're going to look at for this first part of the goals. Okay, so the idea came about that, you know, when they were doing these initial chemistry studies, there's the huge amount of organic chemistry was performed back in the late 1800s. There was a huge industry called the aniline dye industry, where they were learning a whole bunch about chemistry and a whole bunch about different things. But they noticed that certain compounds that had a different smell to them, and that's why they called them aromatic compounds, is that they didn't react the same way that alkenes did, because alkenes reacted kind of, you know, they like to do addition reactions and stuff like that. The benzene systems did not do that. They didn't like to add stuff to them. They like to do substitution chemistry. So there has to be something different here. So the thing that was different is that they figured out that to be aromatic, you have to meet certain rules, okay? And in this rule here, what they figured out was that if you just drew the structure, let me pull up a red pen here. If you just drew the structure of what benzene looked like here, and they figured this out by, you know, how many carbons and hydrogens it had, and the fact that it had a double bond. So they knew these things. And so when they first drew the structure like this, you know, it's like, okay, well, that means that this is a single bond and then this is a double bond. So you should have alternating single and double bonds, and you should be able to see the difference between those. But they couldn't see the difference. And so they said, well, okay, maybe it's not really individual single bonds and individual double bonds. Maybe they're moving back and forth. And so they came up with this kind of rapidly shifting back and forth kind of concept, where, okay, so the double bond is over here, but then it's a single bond, then it's a double bond, then it's a single bond, right? So that kind of explained a lot of things, but that didn't completely account for all the weird reactivity. And so what they came up with the concept of aromaticity. And the idea with the aromaticity was that instead of having localized single bonds and double bonds, or flipping back and forth between them, you actually are sharing the electrons from that double bond across multiple atoms, okay? Just like when we drew resonance structures for, in Lewis dot structures early on, we are doing the same thing. We're gonna spread those electrons out a larger number. okay? So one of the reasons they think it's this way is because when they started doing crystal structures and getting different additional information, is that all of the bond angles within your benzene ring were 120 degrees, and all the bond lengths were identical at 1.39 angstroms long, and all the hydrogen bonds were exactly the same as well. So because everything was the same, that means that at whatever time length that they were doing these measurements, that means that they're moving around so quickly that we can't tell the difference. And so there's this blending of all the substrates and all of the reaction energies. And so what we end up with is that a benzene ring is an aromatic system because of the way it shares the electrons in its p orbital. Notice all of the bonds in the system are sp2 hybridized, okay? So if all those single bonds are sp2 hybridized, that means there's a p orbital on every single carbon in this ring. And that's the cool part about aromaticity, okay? So if we think about all of those carbon bonds as being sp2 hybridized and all the carbon hydrogen being sp2 hybridized, that leaves us one p orbital for each of those carbons, which is a total of 6 p orbitals, okay? Now, if we start doing our Lewis dot structures and count up where all our electrons are, we see that in each one of those p orbitals, there's a single electron, okay? So each of those p orbitals contributes 1 electron to the ring, which means there's a total of 6 pi electrons in that system, okay? And instead of being localized between one and the other, they are continuously moving around and moving around and moving around. So you would think that, oh, I just have a bond here and a bond here and a bond here, and it flips to the other side. Okay, it doesn't do that. What happens is it does what, like this here, it spreads that electron density in a ring out over the entire system evenly. And when it does that, it means all the bonds are exactly the same, all the bonds are exactly the same length and have the same reactivity, okay? So that's what's different about aromatic systems compared to other systems. It's not alternating double and single bonds, it's continuously shared across all of those p orbitals, okay? That being said, there's certain rules you must follow to be able to continuously share these electrons over these double bonds or the pi bonds, okay? So the rules to be aromatic, to have this type of reactivity, okay, you must be in a ring. It can be any size ring as long as it's in a ring, okay? So you can have it 3 atoms to 100 atoms. As long as you follow the rules, it can be aromatic, okay? You must have 1 p orbital on each atom in the ring. Notice it doesn't say carbon, because you don't have to have carbon to have a p orbital, and you don't have to have carbon in every position on the ring to make it aromatic. So the key here is that you have to have a p orbital in that atom. Now notice, I'm not saying you have to have an electron in there either. That orbital can have 1 electron, like in benzene. It can have 0 electrons in it, and I'll show you one of those, or it can have 2 electrons in it. Okay, those are the 3 things that you can have in your p orbital: 1 electron, 2 electrons, or no electrons. So electrons aren't necessary, but p orbital is, for rule number 2. Rule number 3 is it has to be planar or nearly planar. The reason for that is those p orbitals have to be very well aligned to get them to share amongst themselves, right? So we must be in a ring, we must have a p orbital with 1, 2, or 0 electrons in it, and it must be planar so all these p's can overlap continuously, okay? All right, now the last rule, okay? You must have a certain number of electrons, okay? So the total number of electrons in the system has to be what we call 4n plus 2, okay? you don't have to memorize that, but if you could also look at it as that's the number 2, the number 6, the number 10, the number 14, or the number 18, okay? It comes from this 2n, this 4n plus 2 electrons. Now that means that if you have your n is equal to 0, that means you can have a aromatic system with 2 p electrons. And I'm going to show you something that might, I think I show you one that does that. But the most common one is benzene, and benzene has 6 electrons, okay? But once you start fusing benzenes together and other things, you can end up with 10, 14, or 18 electrons, okay? So the key here is ring, p orbital, planar, and the total electrons in those p's has to be 4n plus 2. Most commonly is 6, and I'll show you several examples of that, and I'll show you some couple examples without it. Okay. Okay, so let's do a little little self-quiz here, and we're going to do, is it aromatic? Okay, so let's look at the first thing we have here and see, does it meet all the different requirements here? So I'm going to go back to my pen here, and so our first requirement is it a ring? So this first one we do have a ring, so we meet that requirement, so we do that. Does it have p orbitals? Okay. So the first thing, if we aren't explicitly drawing our p orbitals, look for your double bonds, okay? Is there a double bond on each and every atom in that ring? So you have a double bond here, which means you have to have p orbitals on each of these carbons. So yeah, it has p orbitals that we can put electrons into. Is it planar? Well, yeah, it's planar, okay? So now, does it have that 4n plus 2 pi electrons? Okay, now that's the tricky part. We got to pay attention to when we count these, right? So in a pi bond has 2 pi electrons, right? So if we have 1 pi electron, one pi bond here and 1 pi bond here, each of those pi bonds has 2 electrons, meaning there's a total of 4 electrons in this system, okay? That doesn't fit the rules of 4n plus 2, okay? N has to be a whole number, so we have 2, 6, and 10. Those are the types of electrons we can have. That's the number of electrons we can have, meaning that we don't meet this requirement, meaning this is not aromatic. It met 3 out of the 4 of the requirements, but did not meet that last requirement, okay? So if we look at benzene, we're kind of assuming it's going to be aromatic because that's what we're doing this on, but let's double check it. Is it a ring? Yes. Does it have a p orbital? So there's a double bond here, 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 and here, and here, meaning there's a p orbital on each one of those carbons. So we meet that one. It is planar. We looked at that structure. And let's count the number of electrons. We have a pi orbital here, a pi orbital here, and a pi orbital here. So that's 2 electrons for that double bond, 2 electrons for that double bond, and 2 electrons for that pi bond. So we have a total of 6 electrons. That meets our rule of 2, 6, 10. Okay. Now, I have a question in the chat room. Does the n in 2n plus 4 stand for the number of double bonds? No, it does not. N is just any integer starting from 0, 1, 2, 3, and 4. It's just to signify the number of electrons we have to have in the system. That's why I'm counting our double bonds separately to figure out how many electrons we have. N does not involve the number of double bonds. It's all about our electrons as whole numbers. Okay. So let me back up one thing. I was talking about this with somebody else last week, okay? How many electrons are in a single sigma bond? There are 2 electrons in that single sigma bond, right? That's shared evenly or unevenly between those 2 atoms. So there's 2 electrons in a sigma bond, okay? To have a pi bond, you have to have p orbitals, and typically you have 1 electron in each of those p orbitals overlapping above and below your sigma bond. So your sigma bond has 2 electrons in it, and that pi bond, the one above and below, also has 2 electrons in it. So we can count number of pi bonds when we're counting the total number of electrons, but that is not the same as the n in the 4n plus 2 number. Okay? Okay, so that means this is aromatic because it's a ring. It's got 1, 2, 3, 4, 5, 6 p orbitals. It's planar and it has 6 pi electrons. Okay, let's go to this last one here. This is cyclooctatetraene. So we have 4 double bonds. So let's look at, is it a ring? Yes, it's a ring. Okay. Does it have a p orbital on each one? So we have a double bond on each of these atoms here, meaning we do have a p orbital in each of those atoms there. Is it planar? Actually, it doesn't look planar because it looks like it's pooched up on both ends because it's trying to be sp2 hybridized, and those are 120-degree angles. And so the cyclooctatetraene is actually not planar. So that's one rule it's breaking there. Let's count the number of electrons though, okay? So we have 1 double bond, 2 double bonds, 3 double bonds, 4 double bonds, and a double bond, those p's have 2 electrons, are in that p orbital, that pi orbital. So we have a total of 8 electrons, okay? That doesn't fit our 4n plus 2 rule because it's 2, 6, and 10. Therefore, we actually don't meet 2 of the requirements. We don't meet planar and we don't meet electrons. So that means this is not aromatic. Okay, is everybody kind of got the idea of the 4 rules we're looking for and how to discern them? Okay. Okay, while you're chatting that up in the chat room here, let's go to 3 more and look at whether or not they're aromatic or not, okay? So the first thing we want to look at is we want to look at this cyclopentadiene here. We have some double bonds, so great, you know, we have a ring, all right? So we have ring, okay? And if we look at this, this is sp2 hybridized, sp2 hybridized, sp2 hybridized, and sp2 hybridized, meaning each of those has at least 1 p available, okay? However, this carbon has 2 hydrogens on it and it's sp3 hybridized, meaning it does not have a 2p orbital in it, meaning we've broken this rule here. It is planar and it only has 4 electrons, so we broke that rule too, because 1, 2, 3, 4. We only have 4 of those double bond electrons. So we've broken 2 rules. So that can't be aromatic, okay? So let's look at the next one here. Okay, so now that we have a carbocation here, remember a carbocation is when we've gone to an sp2 hybridized carbon and we have a p orbital, and that p orbital is empty. So there's 0 electrons in it. That's how we get to that carbocation. So now let's look at our rules. We have a ring. Do we have 2 p orbitals on each of those atoms? And the answer is yes on this one, because we have a 2 p orbital on each of these because they're sp2 hybridized. And we have one here, it just has 0 electrons in it, okay? So we have that carbocation, sp2 hybridized, an empty p orbital, okay? So we've met that rule, and it looks planar. Let's count the electrons though. Okay, we have 0 electrons here. We have 1, 2, 3, 4 for those double bonds. We only have 4 electrons in those p's. That means it's not aromatic, okay? Now, let's look at something that's almost identical, except what we have here is the cyclopentadienyl anion. So what that means is that instead of having 0 electrons in this to give us a carbocation, if we put 1 electron in that p orbital, then it would have 0 charge, but it would rehybridize back to sp3, okay? So let's keep that p orbital and add another electron to it. That's gonna give us an anion, okay? That's gonna give us a net negative charge on that carbon, okay? And that means that it's not gonna rehybridize. We actually have a p orbital with 2 electrons in it. Okay, so we have a ring. We have a p orbital on every single one of the atoms in the ring. It's planar, and now let's count our electrons. We have 2 electrons for this double bond, 2 electrons for this double bond, and look, we have a very happy face at the bottom here which means it's 2 electrons for that negative charge in that p orbital. So now we have 6 electrons. So that matches our 4n plus 2 is equal to 6, which means this is aromatic. Okay, so aromaticity doesn't have to be neutral. Aromaticity doesn't have to have only carbon atoms, but you have to meet these 4 rules to get to aromatic things. Okay, so I'm going to throw one more little wrench at you, but it still satisfies all these rules, is the idea of heterocyclic compounds. Okay, hetero meaning different, cyclic meaning a different atom in a ring. Okay, so that's all it really means, is we have something other than carbon in our ring. And we have a lot of these in biological systems, and the 2 I want to start with are things that have nitrogen in them. Okay, so what we're going to do is we're going to look at these compounds and find out whether they're aromatic or not. And whether they're aromatic or not is depending on whether or not they follow these rules. So we can have nitrogen in a ring, but it doesn't have to be aromatic. But when we meet all 4 rules of aromaticity and have a nitrogen in the ring, we now have a heterocyclic aromatic compound. Okay, so let's look at this pyridine here. And so it's in a ring, and notice we have a pi bond here, a pi bond here, and a pi bond here. Okay, so that means we have 6 electrons. Okay, it's in a ring, it's flat. Now, because there's a pi bond, a double bond to this nitrogen, to form that pi bond, that means that nitrogen has to have a p orbital on it. So that's a p orbital, that's a p orbital, p orbital, p orbital. So it meets all 4 rules of having electrons in those pi orbitals. But you say, hey, wait a minute. There's 2 more electrons here on that nitrogen, right? Because nitrogen brings 5 electrons into bonding, right? Where are those 2 electrons? They can't be in the aromatic ring, because that would make it 8 electrons. That would break a rule. So they must be somewhere else, okay? So let's look at where they are, okay? Because that nitrogen was sp2 hybridized to make it trigonoplanar, right? That means we have 1 electron giving us our double bond here and our double bonds here. Let's just freeze them in space for one moment at a time here. Those other 2 electrons are part of the sp hybridized part of the nitrogen, okay? So you have to think, this is part of the sp hybridized, this is part of the sp hybridized. This lone pair is sp hybridized, okay? So it's not a p orbital. Those electrons are isolated in their own hybridized orbital. Therefore, they do not count toward our 4n plus 2 aromatic electrons, okay? So what we see here is that, so nitrogen itself, as long as the atom in the ring is sp2 hybridized and you have a p orbital, it can be aromatic, okay? All right, let me show you a couple other things here that also follow these rules, but look a little different when you first look at them. But when you look at where their electrons are, you'll see where they are. And these next 2 are 2 other aromatic compounds. And I'm going to prove to you that they have 6 electrons and they're in p orbitals, okay? Even though it may look like there's more electrons than they need, okay? So the first one I want to look at here, I want to do this, is furan. So what we have is we still have, if we drew this out, it would look something like this. Right here. So we'd have a carbon-carbon double bond here and a carbon-carbon double bond here, and then we'd have oxygen here, okay? So remember, if that oxygen was sp3 hybridized, it'd have 2 sets of lone pairs, making it bent, okay? But instead, in this particular system, because of the energy saved to make things aromatic, it goes to an sp2 hybridized orbital and puts 2 electrons in that, and then it goes and has that remaining p orbital with those last 2 electrons, okay? So those 2 electrons are in a p orbital. Our oxygen is sp2 hybridized. So now let's count our rules here. We have a ring, we have a p orbital on each of the atoms in the ring. It's planar, and now it has 1, 2, 3, 4, 5, 6. 6 electrons, okay? Because those lone pair are in a p orbital, they count for aromaticity, okay? And we see the exact same thing if we switch that oxygen out for a different nitrogen. Remember in the previous one, in pyridine, we didn't have a hydrogen on here, but we had an sp2 hybridized nitrogen with a lone pair sticking out. In the case of pyrrole, we still have an sp2 hybridized nitrogen, but that third bond is taken up by a hydrogen, and the other 2 bonds are taken up by carbon. And that means the 2 lone pair electrons are now in the p orbital. Notice they're not in the p orbital in pyridine, but you have 5 carbon atoms to donate to the aromaticity. Here, we have 2 electrons in our p orbital, giving us a total of 6 electrons, making it aromatic, okay? So we can extend this out over any number of rings. Notice that this right here, we just did that on the previous page, that half of the molecule is aromatic. And guess what? This half of the molecule is also aromatic, meaning both of those components are going to react as if they were aromatic compounds. Same thing happens here. We have this part is aromatic and that part's aromatic. And notice here, this has 2 different nitrogens here. And notice that each of these nitrogens has a double bond, and there's another double bond over here. That means this is aromatic. And let's see, a double bond here, a double bond here, and a nitrogen with a hydrogen on it means that it has 2 electrons in a lone pair that could be on a p, meaning that part's aromatic as well, okay? So when you're recognizing these heteroaromatic compounds, look for the number of double bonds, and then if your nitrogen, for example, has 3 things bonded to it, that means that lone pair is now in a p orbital. If your oxygen has 2 things bonded to it, it has 1 pair of electrons sticking out in their sp2 hybridized orbital and 1 pair of electrons in that p orbital, okay? So that's what we need to look for when we're looking at, okay, sorry, here it is. That's what we're looking for when we're looking for heteroaromatic compounds. All right, questions on that? Okay, so 4 rules to give us aromaticity. I've shown you how to look for the electrons. They sometimes look deceptively like they're being used somewhere else, but I hope I've proved to you that when you have that lone pair in a p orbital, it'll count toward those aromatic electrons. But when that p orbital is, when those electrons are in that sp2 hybridized orbital, they don't count for counting electrons in your aromaticity. Okay? So go ahead and put something in the Zoom chat there, and then I'm going to move on to our Chapter 9 Goals 2, okay? And it's all about what we call our reagents for our substitution reactions on our aromatic rings, and we call that something else, okay? We call that SNAR, okay? All right, so we're gonna get to there. So up to now, we've been doing what we call nucleophilic substitutions, where we have a nucleophile come in and react with something, or we have addition reactions. Now, with a double bond, we would expect an addition reaction because those are the reactions we learned when we were making alkenes or reacting alkenes, okay? In this case, because the aromatic ring wants to remain aromatic, what it does is it does a substitution reaction, okay? And it does a substitution reaction by having the electrons in the benzene ring reach out and grab something with a positive charge or partially positive charge. And then to re-aromatize, it has to spit out a positive charge. And the most stable positive charge we can spit out is typically the proton, the hydronium atom, proton H+. So most of these reactions, the first step is going to have the formation of something positively charged. The electrons in the aromatic ring are going to reach out and grab that positive charge. And then that ring is going to re-aromatize and spit out a hydrogen. These are the steps you are looking for when we're looking at mechanisms of our electrophilic aromatic substitution, or S for substitution, E for electrophilic, and its substitution reaction on an aromatic ring. Okay, so all of these reactions occur in the exact three-step mechanism. The only thing that changes is whatever the electrophile is, whatever the positively charged species in the reaction is. That's the only thing that changes, okay? So the first thing that happens, we have to create a positively charged species. Now, the one positively charged species we already know about are carbocations, which means we can use carbocations in these reactions. We just have to create them in solution, okay? So, but there are some other positively charged reagents we will be using, and I'll show you those step by step, okay? So the first thing that happens is our aromatic ring, I'm gonna switch over to a red pen here. Our aromatic ring here is now the nucleophile, okay? So this is a little backwards. We usually think, oh, the HBr is gonna add across it or whatever. No, here we are. The electrons in the double bond reach out and create a new sigma bond with that positively charged species, okay? The electrophile, remember it's positive charge, it wants electrons. Our benzene ring has electrons, therefore it's the nucleophile, okay? So it's a slow step to happen, and because we're kind of breaking aromaticity when we do this, that's kind of what we want to think about as why it's the slow step. But once it forms, because we can, by resonance stability, we can have these electrons kick over and move that positive charge to a different part of the ring. And guess what? We can have it happen again and move that positive charge around. By moving this positive charge around, that means that positive charge isn't on the same atom all the time. And therefore, it makes it a little more stable than just having a regular carbocation. So when we rank carbocations, this carbocation is actually more stable than a tertiary carbocation because it's not on one atom, and we're not relying just on inductive effects. We're now relying on resonance stabilization to do it. Notice that our positive charge moves around the ring in a specific pattern. It goes over 2 carbons, and then it goes over 2 carbons. Notice it never shows up back where we had it, right here. It always tries to go over 2 carbons. So that's a pattern you're going to start to see time and time again. Okay, so then the last step is one of those other patterns we were recognizing, which was take a proton away. So that's the easiest way for it to rearomatize, is to have the electrons between the hydrogen and the carbon come back in and form our double bond. And we now have our electrophile is our sp2 hybridized sigma bond. And we've rearomatized our alternating sigma pi bonds right here. And then once the hydrogen leaves, it usually reacts with the base very quickly to get it to go, okay? But the key here is these electrons between the hydrogen and the carbon come back in and regenerate our aromaticity. All right. So that being said, we generate something partially positive. The electrons from the aromatic ring reach out and grab it to generate our carbocation intermediate. And then we lose a positively charged hydrogen to re-aromatize. Those are the 3 patterns we will be using time and time again, okay? We're right at 12:40. So what I'd like to do is I'd like to go ahead and stop recording now answer some questions, and then restart at 12:50, where I look at all the different reagents that are going to follow exactly the same 3-step pattern, where they're just going to change. Okay. All right. I'm going to stop recording.